The universe's greatest builders are microscopic specks of dust. These tiny particles, drifting through the emptiness of space, hold the secret recipe for constructing everything from brilliant newborn stars to entire worlds like our own. We look up at the night sky in wonder, yet we rarely consider that the very substance of those distant suns and planets began as humble cosmic dust. By the end of this journey, you will see the entire cosmos in a completely new way. How can something so small be responsible for such immense celestial structures? And what hidden stories do these particles carry from the depths of ancient stars? What does it mean that our planet, and even we ourselves, were ultimately built from stardust? These microscopic seeds are born from the most powerful events in the cosmos. When a massive star, having burned for millions of years, finally exhausts its fuel, its core collapses in a heartbeat. The resulting shockwave tears the star apart in a supernova explosion, an event so brilliant it can outshine an entire galaxy. In that unimaginable heat and pressure, atoms are fused together into heavier elements, everything from the oxygen we breathe to the iron in our blood. But the story does not end with the blast. As the expanding cloud of stellar debris races outward, it begins to cool. In the dark, frigid reaches of space, individual atoms of silicon, carbon, and iron start to stick together, clustering around microscopic nuclei to form the very first solid particles. This is the moment of creation for cosmic dust. It is a phoenix rising from the ashes, a transformation of scattered energy into tangible matter. Even gentler stellar deaths play their part. Aging red giant stars in their final stages puff away their outer layers in slow, steady winds. These cosmic breezes are laden with newly forged carbon and silicates, providing a continuous, quiet source of raw material. So every speck of dust, whether forged in a violent cataclysm or a serene farewell, carries the elemental signature of a star that lived and died long before our sun was even a glimmer. This is the profound truth behind the phrase "we are made of stardust." The calcium in your bones and the iron in your blood were once forged in the heart of a distant, long-vanished sun. Now, these newly formed particles, these orphans of ancient stars, are about to begin an epic voyage. They will drift for millennia, eventually gathering in vast, dark clouds where the next act of cosmic construction can finally begin. These microscopic travelers do not stay where they are born. Each speck of dust is propelled on an incredible journey, pushed by the gentle but persistent force of starlight itself. Radiation pressure from brilliant young stars acts like an interstellar wind, blowing these particles across the void. They are swept along for thousands, even millions of years, far from the supernova remnants or the fading red giants that created them. Their destination is often a dark, cold molecular cloud, a cosmic nebula so thick with gas and other dust that it blocks the light from stars behind it. Think of these clouds as galactic waste stations, immense and shadowy realms where raw materials slowly accumulate. It is within these murky depths that the next critical phase of growth begins. As dust grains drift through the cloud, they do not travel alone. They bump into one another, and in the cold stillness, a simple but profound physical process takes over. The particles stick together. This is called coagulation. A tiny grain of silicon might collide with a flake of carbon ice, and they fuse. Then this new, slightly larger cluster bumps into another, and then another. Over immense spans of time, microscopic specks slowly, patiently assemble themselves into larger, fluffy aggregates. They are no longer just dust, they are becoming the seeds of something much greater. This growth is not a random free-for-all. The galaxy's own magnetic fields, invisible lines of force that weave between the stars, guide the motion of these particles. Needle-like grains of dust align themselves with these fields, like compasses pointing north, which in turn affects how they move and how they interact with the light passing through the cloud. This constant churning motion serves a grand purpose. It is the galaxy's ultimate recycling program. The heavy elements forged in a star's final moments are not lost. They are carried far and wide, seeding the interstellar medium with the essential ingredients for new solar systems. The iron from a dead star's core and the carbon from a giant's atmosphere are mixed together and delivered to these stellar nurseries. The journey of dust ensures that the death of one star gives life to the next generation. So what happens when this traveling construction material finally settles into a cosmic nursery and begins to build? Deep within these dark clouds, a quiet revolution begins. The very dust that makes the nebula so opaque now becomes the engine of creation. For a star to be born, a cloud must collapse, and this is where dust performs its most vital trick. As gravity slowly pulls the cloud's gas inward, that motion generates heat. Left unchecked, this thermal pressure would push back outwards, fighting gravity to a standstill and halting the entire process. But the dust grains offer an escape route. They absorb this building heat and radiate it away as infrared light, which streams out into space, cooling the cloud's core. It is like opening a pressure release valve on a cosmic scale. This cooling allows gravity to win, letting the cloud condense further and further. Without this dust-mediated cooling, star formation might grind to a halt before it even truly begins. As the density soars in these collapsing pockets, the dust provides the physical anchors for growth. Individual particles act as seeds, giving the surrounding gas something tangible to cling to. Atoms and molecules of hydrogen and helium, which would normally just bounce off each other, instead stick to the surfaces of these dust grains. This makes clumping far more efficient, accelerating the gathering of material. A self-reinforcing cycle takes hold. More mass means stronger gravity, which pulls in even more gas and dust, which in turn increases the density and heat. At the very heart of this swirling, infalling maelstrom, a dense, hot core begins to glow. This is a protostar, a newborn sun still swaddled in its dusty cocoon. Here, the dust performs one more essential duty. It acts as a protective shield. The young stellar object is incredibly vulnerable, and the intense light from other, older stars in the galaxy could easily disrupt its delicate accretion disk. But the thick, dark shroud of dust surrounding the nursery absorbs this external radiation, creating a stable, quiet environment where the protostar can feed and grow in peace. From catalyst to coolant, and finally to protector, cosmic dust is the invisible midwife for stellar birth. And as the new star ignites its nuclear furnace at the center, it leaves behind a rich, swirling disk of leftover material. It is within this disk, this byproduct of star formation, that dust will begin its next, even more intricate construction project, building worlds. With the newborn star blazing at its center, the surrounding disk of gas and dust becomes a cosmic construction zone on a scale we can barely comprehend. This swirling, turbulent protoplanetary disk is where the journey from microscopic speck to full-fledged world truly begins. It starts with a simple, almost gentle process. Those countless dust grains, survivors of stellar explosions and interstellar journeys, are now swirling in a chaotic dance. They bump into each other, and in the low-gravity environment, they do not bounce away. Instead, they stick, held together by weak electrostatic forces, like microscopic bits of fluff clinging to a sweater. This is coagulation, the universe's patient way of building something from almost nothing. These initial collisions create fragile, porous aggregates like cosmic snowflakes. They grow from mere micrometers to centimeters in size, their fluffy structures slowly becoming larger and more complex. But this growth cannot happen randomly. The disk is a dynamic place with gas swirling at different speeds depending on the distance from the star. This creates a sorting mechanism, a natural filter. As these dust aggregates grow, they become less susceptible to the push and pull of the gas. They begin to drift, slowly settling downward, drawn by the collective gravity of the disk itself. They migrate toward the mid-plane, a dense, central layer akin to the settled flour at the bottom of a mixing bowl. This is where the real magic happens. The concentration of solid material in this zone skyrockets. What was once a diffuse haze of dust becomes a crowded highway of growing bodies. Collisions become more frequent and more energetic. The fluffy aggregates pack together, their fragile structures compacting under the increasing pressure. They are no longer just dust bunnies, they are becoming pebbles, then rocks, and then boulders. This is a critical threshold. Once these objects reach sizes of about 1 kilometer, they cross a profound line. Their own gravity becomes significant enough to pull in more material and to hold themselves together against collisions. They have graduated from mere rocks to planetesimals, the fundamental building blocks of planets. These are the embryos of future worlds, and the dust itself is more than just bulk, it is an active chemical factory. In the frigid outer regions of the disk, dust grains act as tiny refrigerated platforms. Atoms and molecules of water, methane, and ammonia that would normally be gas freeze directly onto their cold surfaces, forming thick, icy mantles. These ices become glue, helping smaller particles stick together more effectively, and they also deliver the vital ingredients for water and atmosphere to the growing planetary bodies. Every rocky world from Mercury to Earth and every icy moon in the outer solar system owes its very existence to this humble, incremental accumulation. But what happens when these planetesimals, these kilometer-sized building blocks, begin to interact with each other in the crowded disk? The next stage of construction is far more violent and decisive. This invisible boundary, the snow line, acts as a cosmic dividing line within the swirling disk of creation. Its location is determined by a simple but powerful factor: temperature. Close to the youthful star, intense heat ensures that water, methane, and ammonia remain as gases, but venture beyond a certain radius and the temperature plummets. Here, in the deep freeze of the outer disk, these volatile compounds cannot remain vapor. They flash freeze directly onto the surfaces of every dust grain they encounter. A microscopic speck of silicate or carbon, once dark and dry, suddenly finds itself encased in a thick, glistening mantle of ice. This transformation is not just cosmetic, it is a fundamental game changer for planet formation. The ice acts as a powerful adhesive. When two icy dust grains gently collide, they do not bounce apart, they fuse together, held fast by their sticky coatings. This makes the process of coagulation immensely more efficient beyond the snow line. Growth accelerates at a staggering pace. What begins as tiny, icy specks rapidly snowball into larger and larger aggregates, then into massive icy planetesimals. These are no mere rocks, they are frozen worlds in the making, some growing to be 10 times more massive than their rocky cousins closer to the star. This immense mass gives them a gravitational advantage. They begin to act as gravitational anchors, pulling in the vast reservoirs of hydrogen and helium gas that still swirl throughout the disk. This is the birth of a gas giant. A massive, icy core serves as the seed around which a planet like Jupiter or Saturn accumulates its enormous gaseous atmosphere. Without that initial icy core built upon a foundation of dust, such a giant could never form. But the influence of these icy bodies does not end there. They are also the primordial source of comets. Many of these frozen planetesimals were never incorporated into large planets. Instead, they were flung into the outer darkness by gravitational interactions, becoming the denizens of the distant Oort cloud. Throughout the life of a solar system, some of these icy wanderers are nudged back inward, falling toward the star as spectacular comets. When they travel into the inner system, they bring with them a precious delivery: water, ice, and complex organic molecules. The very water that fills our oceans and the carbon-based ingredients that seeded life on Earth were likely delivered by comets, icy messengers from beyond the snow line. And so, the simple presence of dust, acting as a platform for ice, directly dictates the entire architecture of a planetary system. A temperature gradient, working in concert with these tiny particles, creates the stark division between the small, rocky inner planets and the giant, gaseous outer worlds. It is a profound demonstration of how a universal rule, applied to a cloud of dust, can yield the beautiful diversity we see in the cosmos. From this chaotic disk of gas and dust, the final, familiar shapes of planets begin to take form. The inner disk is a forge of fire and rock. So close to the young star, temperatures are far too high for delicate ices to survive. Only the most resilient materials can endure this blistering environment, the cosmic survivors known as refractory elements. Here, dust is not fluffy ice but hardy grains of silicates, the stuff of sand and stone, and flecks of heavy metals like iron and nickel. These are the fundamental bricks for building terrestrial worlds. Their growth begins gently, with microscopic particles colliding and sticking in the chaotic dance of the disk. But this process soon escalates into something far more dramatic. Through a mechanism called runaway growth, a few fortunate planetesimals gain a slight size advantage. Their slightly stronger gravitational pull allows them to attract more material, growing faster than their smaller neighbors. They become the dominant bullies in the celestial playground, sweeping up smaller rocks and dust in their path. This stage of planetary construction is anything but peaceful. It is an era of colossal, violent collisions, a chaotic demolition derby where protoplanets the size of Mars or larger smash into one another in titanic mergers. The energy released in these impacts is staggering, melting entire worlds and reshaping them completely. Within these molten spheres, a profound sorting process begins. This is differentiation. Heavier elements, primarily iron and nickel, sink through the liquid rock, drawn by gravity to form a dense metallic core. Lighter silicate minerals rise to the surface, eventually cooling to form a solid crust and a thick mantle. This is how a planet finds its structure, creating the layered architecture we see in Earth today. Every solid surface in our solar system, from the cratered plains of Mercury to the towering volcanoes of Mars, is a direct result of this hierarchical accumulation. Our Earth, with its protective magnetic field generated by a swirling iron core and its solid crust that provides a foundation for life, was built piece by piece from this ancient cosmic dust. The very ground beneath your feet is a monument to that violent and creative era. But what specific gifts did this stardust deliver to make our world not just a rock but a living planet? But cosmic dust offered a final, priceless gift beyond the planet's physical structure. These tiny particles served as microscopic delivery vehicles, carrying the essential ingredients for life itself across the solar system. Out in the cold, dark molecular clouds where stars are born, dust grains act as miniature chemical laboratories. Their surfaces provide a solid platform where simple atoms and molecules can meet and react. Water, ice, and other frozen gases coat these specks, forming complex icy mantles. When bathed in the faint ultraviolet light from distant stars, a quiet alchemy occurs. This energy catalyzes chemical reactions on the dust grain surfaces, forging complex organic molecules, including the amino acids that are the fundamental building blocks of proteins. This means that long before our solar system even existed, the raw chemical precursors for life were already being assembled on particles of interstellar dust. When our own solar system coalesced, these pre-processed grains were incorporated directly into the mix. They became part of the comets and icy asteroids that formed beyond the snow line. For hundreds of millions of years after the Earth's formation, our planet endured a period known as the Late Heavy Bombardment. The inner solar system was a shooting gallery, with a vast rain of comets and asteroids striking the young worlds. For a dry, rocky Earth, this was a transformative deluge. These impacting bodies, themselves built from ancient dust, shattered upon arrival, releasing enormous quantities of trapped water vapor into the nascent atmosphere. Over time, this water condensed and fell as rain, slowly filling the vast basins that would become our oceans, but they delivered more than just water. Locked within their icy cores were those complex organic molecules manufactured on dust grains in interstellar space. The very dust that built our world also seeded it with water and the chemical blueprints for biology. We are not just made of stardust, our living planet was awakened by it. This profound connection raises an obvious question. Can we see this cosmic courier in action today, still performing its ancient role across the galaxy? Yet we are not blind to these tiny architects. Astronomers have developed brilliant methods to observe the unseeable, to trace the faint signature of dust across the cosmos. Since a single speck at such vast distance is invisible, they instead watch how dust alters the light that passes through it. When starlight travels through a cosmic cloud, the dust within acts like a fine haze. It scatters the blue light more effectively than the red, causing the distant stars to appear both dimmer and redder than they truly are. This phenomenon, called interstellar extinction, is a telltale sign of an invisible veil of dust hanging between us and the star. But dust does not only hide things, it also reveals itself by glowing with a heat we cannot see. Warmed by the very starlight it absorbs, each dust grain radiates that energy back out as infrared light. Our eyes are blind to this thermal signature, but our telescopes are not. Space-based observatories like the James Webb Space Telescope are essentially powerful heat detectors, peering into the hearts of dark nebulae to see the faint infrared glow of the dust itself, illuminating the very structures where new stars are being born right now. There is another subtle clue hidden in the starlight, a quality known as polarization. As light travels through space, its waves normally vibrate in all directions. But when it passes through a cloud filled with elongated, needle-like dust grains, something changes. These grains tend to align themselves with the galaxy's magnetic fields like countless tiny compasses. This alignment forces the starlight to vibrate in a more preferred direction, polarizing it. By measuring this polarization, astronomers can not only detect the dust, but also map the invisible magnetic fields that shape the cosmos. For the most direct evidence of all, scientists go hunting. High-altitude aircraft soar into the stratosphere, trailing collectors designed to catch the finest of particles. These are interplanetary dust particles, or IDP, microscopic specks that continuously rain down on Earth from space. Capturing them is like collecting snowflakes from a blizzard, but these are snowflakes from the depths of the solar system. In laboratories, these precious grains are analyzed, revealing their complex structure and ancient composition. They are tangible pieces of the cosmic construction material, and they tell us that this dust is not a distant abstraction. It is a substance that falls upon our world even now. Each of these techniques, from studying altered starlight to catching particles from the sky, builds an undeniable case. Dust is everywhere, a fundamental component of the galaxy's structure and the silent partner in the birth of every star and planet. This observational proof transforms a beautiful theory into a concrete reality, confirming the profound and overlooked power of the microscopic specks that built our cosmic home. Even our own solar system is veiled in a permanent, ethereal glow. Just after sunset or before sunrise, under perfectly dark skies, you can sometimes see a faint, cone-shaped light rising from the horizon. This is the zodiacal light, a soft luminescence caused by sunlight scattering off countless trillions of dust particles. These particles form a vast, dusty disk that sprawls across the inner solar system, all orbiting in the same flat plane as the planets. This is not a static cloud, but a dynamic population. It is constantly replenished by the gradual disintegration of comets, which shed dust as they swing near the sun, and by the occasional shattering collision between asteroids in the belt between Mars and Jupiter. This gentle glow is a visible echo of the violent and creative processes that built our planetary neighborhood, a reminder that construction and destruction are two sides of the same cosmic coin. The sources of this dust extend far beyond what we can easily see. Out past the orbit of Neptune lies the Kuiper Belt, a vast realm of icy remnants left over from the solar system's formation. Even farther, in the deep freeze at the solar system's edge, is the theorized Oort cloud, a spherical shell of icy planetesimals and dust. These are the cold storage lockers of our solar system, preserving the original material from which everything here was made. We have not had to simply theorize about this dust, we have reached out and touched it. NASA's Stardust mission performed an incredible feat of cosmic retrieval, flying through the coma or dusty envelope of a comet. It used a special substance called aerogel, an ultralight material that acted like a cosmic smoke catcher, gently trapping speeding particles of cometary dust. When the spacecraft returned these samples to Earth, scientists held in their hands pristine material that had been untouched since the dawn of our solar system. Analyzing these grains provided a ground truth, a definitive reference for what primordial cosmic dust is actually made of. This local knowledge is our Rosetta Stone. When we peer at distant stars and see similar disks of dust, we are no longer just guessing at their composition. We can compare them to the dust right here in our own cosmic backyard. This tells us that our solar system is not a unique, finished artifact. It is one dynamic example of an ongoing, universal process. The faint zodiacal light is our personal connection to this grand cycle, a daily reminder that we live inside a system still breathing with the dust of its own creation. These glowing disks around young stars are not just beautiful, they are active planetary construction sites. When we peer into a nebula like Orion, we are seeing the future. Each disk is a snapshot of a solar system being born, a dynamic arena where gravity and dust are collaborating to build new worlds. The most telling clues are the dark rings and bright gaps that appear within these disks. These are not empty voids, they are the gravitational signatures of infant planets, sweeping their orbits clear of dust and gas as they grow. A young planet's gravity acts like a cosmic snowplow, pushing material aside and carving out a distinct path around its star. This process leaves a visible fingerprint, a ringed pattern in the disk that our most powerful telescopes can now detect. The dust within these disks tells its own complex story. It is not a uniform haze. Close to the star, the dust is dominated by hardy silicates and metals that can withstand the heat. Farther out beyond the snow line, these same particles are encased in thick layers of ice. This variation in composition and the size of the dust grains creates entirely different environments for planet formation. In one region, you get the ingredients for small, rocky worlds. In another, you get the sticky, icy seeds for gas giants. By analyzing the light from these disks, astronomers can read this chemical map. They can determine what materials are available and where, allowing them to predict what kinds of planets might emerge from the chaos. This makes every protoplanetary disk a celestial Rosetta Stone. It translates the fundamental laws of physics and chemistry into the vast diversity of planetary systems we observe. We are no longer just theorizing about how our solar system came to be. We are watching the same process unfold around other stars. This direct observation confirms that the humble journey of dust from stellar ash to planetary block is a universal story. Every gap and ring we see is a testament to the ongoing creative power of the cosmos, building new worlds one speck of dust at a time. Yet even these resilient specks are not permanent. The cosmic dust that builds worlds is itself caught in a relentless cycle of creation and destruction, a galactic rhythm that ensures no particle rests for long. New dust is constantly being forged in the furnaces of dying stars, but old dust is just as constantly being dismantled. In the harsh environments of space, a dust grain faces many threats. When a supernova shockwave, traveling at millions of miles per hour, slams into a cloud of dust, it acts like a cosmic sandblaster. The high-energy collisions literally shatter the grains, blasting individual atoms back into the gaseous void from which they came, a process known as sputtering. In regions illuminated by brilliant, hot young stars, intense ultraviolet radiation bombards the dust. This relentless energy barrage can heat the grains until they evaporate, their substance returning to the interstellar gas. And sometimes the dust meets its end by succeeding in its ultimate purpose. When a speck is permanently incorporated into a planet or a large asteroid, its journey is over. It is taken out of the interstellar cycle, locked away in a rocky world for billions of years. This constant tug of war between production and destruction sets the overall abundance of dust we see in any galaxy. This balance is not a minor detail, it is a fundamental governor of galactic evolution. The amount of dust available directly regulates how quickly new stars can form by cooling clouds, and it controls how heavy elements are mixed back into the raw material of the galaxy. The lifespan of an individual dust grain may be fleeting, perhaps only tens of millions of years, a mere blink in cosmic time. But in that brief window, it holds the potential to catalyze the birth of a star and become part of a new world. This endless cycle is the galaxy's way of recycling its most precious resources, ensuring that the ashes of dead stars will always be available to build the next generation of cosmic wonders. This delicate interplay between dust and light profoundly reshapes our view of the cosmos. The universe we see is not the universe as it truly is, but a version filtered through a vast, invisible lens of microscopic grains. A star's brilliant white light, traveling for hundreds of years, does not arrive at our telescopes unchanged. As it passes through clouds of cosmic dust, the blue wavelengths of light are scattered away, much like our own sky scatters sunlight to create its familiar blue hue. The redder light, however, pushes through more easily. The result is that the star appears to us not as a brilliant diamond, but as a dimmer, redder gem. This effect, called interstellar reddening, means many of the stars we admire for their warm, ruddy glow are actually blazing white or blue in reality, their true colors muted by a cosmic veil. This dimming and reddening, collectively known as extinction, presents a fundamental challenge for astronomers. To understand a star's true distance, age, and size, we must first know its intrinsic brightness. If we do not correct for the dust that dims its light, our calculations about the scale of the galaxy and beyond can be thrown completely off course. It is a constant, meticulous process of cosmic detective work, peeling back the dusty layers to see the universe beneath. Yet this dusty filter is not only an obstacle, it can also be an artist. In a reflection nebula, the process is reversed. Here, a cloud of dust sits close to a brilliant, hot star. Instead of absorbing the light, the dust grains scatter it, and they are far more efficient at scattering blue light. This paints the entire cloud in a spectacular, ethereal blue glow, like cosmic fog illuminated by a celestial spotlight. The iconic blue haze surrounding the Pleiades star cluster is not gas itself glowing, but simply starlight being reflected by a chance cloud of dust. This beautiful phenomenon gives us a direct visual map of where this cosmic material resides. By carefully measuring both the reddening of background stars and the polarization of their light, scientists can reconstruct a three-dimensional map of dust distribution throughout the Milky Way. They can determine the size, composition, and even the orientation of these tiny grains. The light that reaches our eyes and our telescopes is not a pure signal, but a message that has been encoded by its journey through the dusty interstellar medium. Learning to read that code reveals the hidden architecture of our galaxy. These frigid, dark clouds are far from empty, they are bustling chemical hubs. But the chemistry that occurs here is unlike anything on Earth, taking place on the most unlikely of platforms, the surfaces of cosmic dust grains. In the diffuse void between stars, atoms and simple molecules drift alone, rarely meeting with enough energy to form lasting bonds. But inside a dense molecular cloud, everything changes. A wandering hydrogen atom, for instance, does not simply bounce off a dust grain. Instead, it sticks, held fast by weak intermolecular forces in a process known as adsorption. Soon, another atom joins it and another. The frigid surface of the grain becomes a crowded dance floor for simple ingredients. The extreme cold is the key. It slows the atoms down just enough that they can slide and migrate across the grain's surface, searching for a partner. When two hydrogen atoms finally meet, they link up, creating a molecule of hydrogen gas, H2. This seemingly simple handshake is a cosmic bottleneck. In the emptiness of space, forming a hydrogen molecule from two lone atoms is incredibly rare and inefficient. But on a dust grain, it happens with astonishing ease. This is the universe's primary method for creating the molecular hydrogen that fuels the formation of new stars. The process does not stop there. More complex guests arrive at this microscopic party. Atoms of oxygen and carbon, along with molecules like carbon monoxide, also freeze onto the dust. Their interactions, guided by the unique landscape of the grain's surface, build upward in complexity. Water ice begins to form in layered mantles. Through a series of surface reactions, simple carbon-based molecules can assemble into more complex organic compounds, things like methanol and formaldehyde. These are the molecular precursors to the building blocks of life. For millions of years, these icy dust grains act as frozen chemical libraries, silently storing this newfound complexity. Then a star is born. The heat and light from the newborn sun rush through the cloud, warming the dust grains. This sudden input of energy is like a starting pistol. The icy mantles evaporate, releasing their stored treasure of newly forged molecules back into the surrounding gas. This enriched material then becomes part of the swirling protoplanetary disk, delivering water and probiotic chemicals directly to the regions where planets are assembling. Without this quiet, patient chemistry on a speck of dust, the universe would be a much simpler and far less interesting place. The journey from a solitary atom to the chemistry of life begins on these microscopic platforms, the universe's most overlooked and essential laboratories. These microscopic diamonds and specks of silicon carbide are the oldest solid materials you could possibly hold. They are presolar grains, tiny messengers from a time before our sun even existed. Locked inside certain primitive meteorites, these particles have survived an almost unimaginable journey. They formed in the atmospheres of ancient, dying stars, were ejected into the galactic void, and then endured the violent, chaotic maelstrom of our own solar system's birth. Against all odds, they arrived here unchanged. Each one is a time capsule sealed billions of years ago. When scientists analyze these grains with incredibly precise instruments, they are not just studying dust, they are reading the autobiography of a star. Every grain carries a unique isotopic signature, a chemical fingerprint that reveals its origin. The specific mix of elements in a single microscopic diamond can tell researchers whether it was forged in the gentle, windswept atmosphere of a red giant or in the cataclysmic inferno of a supernova. This is direct evidence, a piece of a star we can hold in a laboratory. It transforms stellar nucleosynthesis from a theoretical model into a tangible reality. We have in our hands the very elements that were cooked in the heart of a star that died before our solar system was even a cloud of gas and dust. The survival of these grains is a testament to their incredible resilience. They drifted through the primordial solar nebula as it collapsed, avoiding being vaporized in the heat of the young sun's birth. They were present as planetesimals smashed together, and they endured being locked away inside asteroids for eons. Their journey did not end until that asteroid fell to Earth, delivering its precious cargo. By collecting and studying these presolar grains, we are effectively doing something profound. We are conducting interstellar archaeology. We are sifting through the cosmic rubble to find artifacts from other suns. This gives us a direct window into the galactic environment that gave rise to our solar system. It tells us what kinds of stars contributed their dust to our particular mix, painting a picture of the stellar neighborhood that existed here long ago. These tiny, indestructible specks are the ultimate record keepers, silently preserving the history of our galactic origins within their crystalline structures. This cycle of dust production and destruction is not a local phenomenon, it is the engine of galactic evolution. A galaxy is not just a collection of stars, it is a complex ecosystem, and cosmic dust is one of its most vital nutrients. This entire process began in the profound emptiness of the early cosmos. The very first stars to ever ignite were behemoths, composed only of the primordial elements hydrogen and helium. These titans, known as population 3 stars, lived fast and died young in spectacular supernovae. In their violent deaths, they achieved something unprecedented. They forged the universe's first heavy elements, and they scattered the very first seeds of cosmic dust into the void. This was a pivotal transformation for the cosmos. The universe was no longer pristine, it was now enriched. When the next generation of stars began to coalesce, they formed from clouds that already contained these precious heavy elements and dust grains. This changed everything. The presence of dust made the gas clouds far more efficient at cooling, allowing gravity to pull them together faster and more effectively. Star formation was no longer a sluggish struggle. It could now accelerate, building galaxies with breathtaking speed. In the modern universe, we see this power in its most extreme form. So-called starburst galaxies are colossal cosmic factories, churning out new stars at a ferocious rate. These regions are so thick with dust that the brilliant light from millions of newborn stars is almost completely absorbed. To our optical telescopes, these areas can appear as dark, quiet voids. But when we look with infrared eyes, the truth is revealed. The dust itself glows with the trapped heat of that hidden stellar fire, revealing a frenzy of creation happening behind the scenes. Dust also governs the graceful exit of stars. In the final stages of their lives, aging stars gently blow their outer layers into space through steady winds. These cosmic breezes are laden with freshly manufactured carbon and silicate dust, a final gift to the galactic reservoir. This continuous cycle of expulsion and enrichment, driven by dust, ensures that the raw materials for new stars and planets are never depleted. The life cycle of a single speck of dust is therefore woven into the grandest narrative of all, the birth, maturity, and eventual quieting of an entire galaxy. It is a fundamental component in a story of cosmic renewal that spans billions of years. Hidden within the very colors of starlight is a chemical mystery over a century old. When astronomers break that light into a rainbow spectrum, they find hundreds of tiny, dark lines etched into it at precise, unyielding wavelengths. These are the diffuse interstellar bands, and they are the signature of an unknown substance soaking up specific parts of the light as it travels through space. For all our knowledge of cosmic dust, the true identity of this cosmic thief remains one of the great unsolved puzzles in all of science. The most compelling clue is that these absorption features are strongest in regions rich with dust and complex carbon, pointing toward large, intricate molecules as the likely culprits. Imagine a vast, invisible sea of organic compounds drifting between the stars, each one a complex structure built around chains or rings of carbon atoms, perhaps even clinging to the surfaces of dust grains for stability. These molecules are not life itself, but they are the sophisticated chemical Lego bricks from which biology could one day arise. Their sheer variety, hinted at by the hundreds of different absorption lines, suggests a level of molecular diversity in deep space that we are only beginning to appreciate. Why does this mystery matter so profoundly? Because these unknown carriers represent a massive, hidden reservoir of organic material, a significant fraction of all the carbon in our galaxy. Unlocking their chemical identity would be like finding a key to a secret library, revealing the full inventory of complex chemistry that dust helps to create and protect. Every dark line in a stellar spectrum is a question waiting for an answer. It asks what molecule is floating out there, how it formed, and what role it plays in the grand cycle of cosmic material. Solving this riddle would not just put a name to an abstract line on a graph. It would complete a crucial chapter in our understanding of how the universe builds chemical complexity from stardust. It is a humbling reminder that for all our telescopes and technology, the space between the stars still holds profound secrets, and the most fundamental builders of our cosmos are still, in many ways, unknown to us. Even in the universe's most ferocious realms, dust does not merely survive, it thrives. Picture the environment around a supermassive black hole, a place of unimaginable gravitational fury and searing radiation. Here, vast quantities of dust and gas are whipped into a colossal, donut-shaped structure called a torus. This isn't a placid cloud, it's a frenzied, spinning whirlpool of material feeding the central monster. As the dust spirals inward, it is compressed and heated to incredible temperatures, yet it plays a crucial role in this violent drama. The torus actually helps funnel matter onto the black hole's accretion disk, and in doing so, it also masks the brilliant core from certain angles, shaping the intense beam of light we observe as a quasar. This dust isn't a passive bystander, it is an active participant, helping to regulate one of the most energetic processes in the cosmos. Similarly, dust emerges from total annihilation. When a massive star explodes as a supernova and leaves behind a super-dense, spinning neutron star, the expanding shell of debris is a cauldron of newly forged heavy elements. In the years following the blast, as this cloud expands and cools, astronomers have witnessed a remarkable rebirth. Tiny specks of dust, primarily silicates and carbon, begin to condense from the vaporized gas, much like soot forming in a cooled flame. This is dust forming in the aftermath of its own creator's death, a testament to the relentless cycle of cosmic recycling. The very presence of these grains in such hostile territory, buffeted by intense radiation and gravitational tides, speaks to a fundamental resilience. Studying this dust gives us a unique probe into the extreme physics at work. Its composition and survival tell us about the conditions inside a supernova and the powerful winds streaming from neutron stars. From the serene stellar nurseries to the chaotic frontiers around black holes, dust is a universal constant, a humble but indomitable material that endures from one cosmic extreme to the next. This profound connection between dust and destiny brings us to a humbling truth about our own place in the cosmos. The specific chemical elements that compose our bodies, the carbon in our cells, the oxygen we breathe, the nitrogen in our DNA, were all forged in the hearts of distant, long-dead stars. It was cosmic dust that served as the galactic courier, distributing these essential ingredients across the void and delivering them to the nascent cloud that would become our solar system. Without this precise elemental delivery service, the raw materials for life would have remained scattered and inaccessible. The entire architectural process of building a planet, from the gentle sticking of microscopic grains to the violent collisions of protoplanets, was orchestrated to create a stable, rocky world. Our Earth formed at that perfect, narrow distance from the Sun where water could persist as a liquid, a rare and precious zone enabled by the gradual accumulation of this stardust. And the final, vital gifts arrived aboard comets and asteroids, themselves constructed from that same ancient material. These icy messengers brought the water that fills our oceans and the complex organic molecules that seeded our biochemistry. If any single property of cosmic dust had been different, if the grains were too smooth to stick, or their surfaces were inert and unable to host chemical reactions, the entire chain of events could have faltered. Our solar system might be a collection of barren rocks, or it might not have formed at all. This realization weaves humanity directly into a cosmic narrative billions of years in the making. We are not merely observers of the universe, we are a product of its most fundamental processes. Our existence is a testament to a chain of cosmic events so precisely tuned that the most humble of materials, a speck of dust, could ultimately lead to a world teeming with life. It invites a moment of quiet reflection on our own origins and on the incredible journey that connects every one of us to the stars. The next decade will bring our understanding of cosmic dust into sharper focus than ever before. A new generation of observatories and missions, equipped with revolutionary technology, is turning its gaze toward these microscopic architects. The James Webb Space Telescope, with its extraordinary sensitivity to infrared light, is already acting as a cosmic heat detector. It peers directly into the dense, dusty hearts of stellar nurseries and the swirling disks around young stars, seeing the warm glow of the dust itself. This allows us to witness the chemical and structural details of planetary construction zones as never before, watching the very process of world building unfold in real time around other suns. But our investigation will not stop at simple observation. Future missions are designed to be cosmic detectives, uncovering the direct links between dust and planets. The European Space Agency's Ariel telescope, for instance, will specialize in analyzing the atmospheres of distant exoplanets. By studying the chemical makeup of these alien skies, scientists can trace the elements back to the specific types of dust that coalesced to form those worlds, revealing the unique recipe for each solar system. The quest for direct samples is also accelerating. Ambitious proposed missions aim to do more than just fly by a comet. They plan to capture material directly from the erupting plumes of icy moons like Enceladus. These geysers are thought to blast particles from a hidden ocean into space, offering a potential sample of a watery world and the dust within it. Another dream is a full-scale sample returned from a comet nucleus, bringing back pristine, frozen material from the solar system's birth, untouched by Earth's environment. Meanwhile, back in laboratories on Earth, the tools for discovery are becoming astonishingly precise. Scientists can now analyze individual presolar grains, those ancient time capsules from other stars, atom by atom. This allows them to read the stellar autobiography locked within each speck with a clarity that was once pure science fiction. Together, these efforts are weaving a rich, detailed tapestry of knowledge. They are transforming cosmic dust from a theoretical component of our models into a tangible, well-understood character in the story of our cosmos. We are on the verge of answering some of our most fundamental questions, not through inference but through direct encounter. The path forward is illuminated, promising to show us not just where we came from, but how common our own world story might be across the galaxy. A perfect vacuum is a myth. While the space between stars is emptier than any chamber we can create on Earth, it is far from truly empty. This interstellar medium is a diffuse soup of gas and countless dust grains, with densities so low they are almost impossible to comprehend. In a volume of space as large as a typical skyscraper, you might find only a few solitary atoms and a handful of microscopic dust specks. Yet across galactic distances, this sparse haze accumulates into a powerful cosmic presence. This leads to another common misunderstanding, that this dust is merely a cosmic irritant, an obscuring curtain that frustrates astronomers. It is true that dust blocks our view of the universe's most luminous regions, but seeing it only as a nuisance is like complaining about the scaffolding surrounding a magnificent new building. That very scaffolding is what allows the structure to rise. Without dust to cool molecular clouds and seed the growth of planets, the brilliant stars and worlds we long to see would never have formed in the first place. The dust is not an obstruction to the view, it is the reason there is a view at all. We also tend to picture these grains as simple, like tiny motes of household dust. The reality is far more intricate. Cosmic dust is a material scientist's dream, a menagerie of bizarre shapes and structures. Some grains are jagged and amorphous, like shattered glass, while others possess near-perfect crystalline lattices, miniature diamonds forged in stellar furnaces. They can be fluffy, porous aggregates, more empty space than solid material, or they can be needle-like filaments aligned by magnetic fields. Their composition is just as diverse, ranging from silicates, the stuff of rock and sand, to carbon-based grains resembling soot, and even ices of water and methane frozen into solid mantles. Another persistent idea is that all cosmic dust is ancient, a static relic from the early universe. In truth, the population of dust is dynamic and constantly turning over. New dust is ceaselessly being manufactured in the atmospheres of aging stars and in the expanding remnants of supernovae. Simultaneously, old dust is being destroyed, vaporized by shock waves or evaporated by intense radiation. The dust we see represents a balance between these ongoing processes of creation and destruction, a galactic ecosystem in constant flux. Perhaps the most significant misconception is to dismiss dust because of its small, individual size. This ignores the profound power of collective action. A single dust grain is insignificant, but trillions upon trillions of them, working together across billions of years, have sculpted the visible universe. They have filtered the light of galaxies, governed the birth rate of stars, and provided the raw material for every planet. Their small size is their greatest strength, granting them a cumulative influence that no single large object could ever possess. Correcting these myths is not just an academic exercise, it reshapes our entire cosmic perspective, allowing us to see the universe not as a collection of isolated objects, but as an interconnected system built and shaped by its smallest components. The cosmos is an artist, and its primary medium is the same dust that builds its worlds. Some of the most iconic celestial portraits are painted by emission nebulae, vast clouds of gas and dust energized by the fierce ultraviolet light of newborn stars. The radiant glow of the Orion Nebula is a stellar nursery lit from within, its hydrogen gas fluorescing like a cosmic neon sign. Yet for all their brilliance, these nebulae gain their texture and depth from the dust woven throughout. It is the dust that creates the dark lanes and dramatic shadows, carving intricate structures out of the luminous gas and giving the scene a breathtaking three-dimensional quality. Contrast this with the stark beauty of a dark nebula like the Horsehead. Here, there is no internal fire. Instead, we see a colossal, silhouetted cloud of cold, dense dust, a cosmic sculpture etched against the bright background glow of ionized gas. Its famous shape is not permanent. It is a fleeting moment in an epic story, as the stellar winds from nearby stars slowly erode the cloud, revealing the newborn stars hidden within. Then there are the reflection nebulae, which possess an almost ghostly elegance. The delicate blue haze enveloping the Pleiades star cluster is not generated by the stars themselves. It is starlight scattered by a chance cloud of dust, a celestial fog bank reflecting the brilliant blue light of the cluster's hottest stars. This selective scattering, the same phenomenon that makes our own sky blue, paints these clouds in the most serene shades of cosmic cobalt. These structures are far from static. Their ethereal forms are constantly sculpted and reshaped by the very stars they help to create. The intense radiation and powerful stellar winds from massive stars act as cosmic chisels, carving away at the surrounding dust, blowing vast bubbles, and compressing nearby material to trigger the next wave of star formation. This is a dynamic feedback loop, where one generation of stars uses the dust from its ancestors to shape the environment for its descendants. The universe is not merely functional, it is profoundly beautiful, and that beauty emerges directly from the physics of light interacting with microscopic particles. The grandest nebulae are a testament to this artistry, reminding us that the same humble dust that constructed our planet is also the paint on the galactic canvas. This gentle rain of cosmic dust is a constant feature of our planet's environment. Every single day, Earth accumulates tons of fine particulate matter from comets and asteroids, a silent, invisible influx from space. These interplanetary dust particles are so small they drift down through the atmosphere without burning up, settling as a microscopic mist. Once aloft, they perform a subtle but significant role. In the cold, thin air of the upper atmosphere, these specks act as ready-made nuclei. Water vapor freezes directly onto their surfaces, forming wispy, high-altitude ice clouds known as noctilucent or polar mesospheric clouds. The presence and density of these ethereal clouds can influence how much solar energy is reflected back into space or trapped within our atmosphere, creating a delicate link between cosmic dust and our planet's climate dynamics. The influence of dust is even more dramatic on our neighboring world. Mars is a planet practically defined by dust. Its thin atmosphere can host storms that begin as a local gust and within weeks grow to envelop the entire globe. These planet-wide events blot out the sun, dramatically altering surface temperatures and reshaping weather patterns for months. The dust itself becomes the central player in the Martian climate system, absorbing solar radiation and heating the atmosphere, which in turn drives powerful winds that lift even more dust, a self-sustaining cycle that transforms the entire face of the planet. Beyond their physical presence, these particles are also chemical messengers. The dust constantly settling through our skies carries trace amounts of metals like iron and nickel, along with other compounds. When this dust drifts down over the oceans, the iron it contains can act as a vital nutrient, fertilizing phytoplankton blooms that draw carbon dioxide from the atmosphere and form the base of the marine food web. This ongoing delivery represents the modern, gentle version of a process that was critical in the early solar system. During that formative era, the relentless accretion of dust provided a steady supply of water and other volatile elements to the young, rocky planets, contributing directly to the inventory of substances that would one day form our oceans and atmosphere. So the relationship between a world and cosmic dust is not a singular, ancient event locked in the distant past. It is a continuous, living interaction. The microscopic dust falling on Earth today is a faint whisper, a quiet echo of the colossal downpour that once assembled our planet from nothing but stardust and gravity. The hunt for these cosmic builders brings us from the vastness of space to the quiet confines of a laboratory. Scientists are actively collecting extraterrestrial dust that has journeyed across the solar system to land on our world. Specially designed aircraft flying high in the stratosphere extend collectors with ultra-sticky surfaces to capture these microscopic travelers as they drift down through the atmosphere. Other researchers search for them in the pristine ice of Antarctica and in the layers of deep-sea sediments, where the particles have slowly accumulated over thousands of years, creating a natural archive of cosmic fallout. Each recovered speck is a precious piece of the puzzle, a direct sample from the distant past. Back in the lab, under the beam of an electron microscope, these grains reveal a hidden universe of form. They are not uniform motes, but a stunning menagerie of shapes, from intricate, fluffy aggregates that look like cosmic snowflakes to solid, geometric crystals forged in stellar furnaces. The most profound analysis happens when scientists probe their elemental heart. Using incredibly sophisticated instruments, they can measure the precise isotopic composition of a single grain. These isotopes are the ultimate fingerprint, a chemical signature that reveals whether the dust was born in the gentle outflow of a red giant star, the violent explosion of a supernova, or another exotic stellar environment. This highly specialized field, known as micrometeoritics, provides the essential ground truth that confirms and refines our telescopic observations of the cosmos. To protect the integrity of these ancient messages, every step is taken in ultra-clean rooms, where the very air is filtered to prevent any earthly contamination. This meticulous work transforms an abstract idea into a tangible reality, allowing us to hold a piece of stellar history in our hands and read the autobiography of the stars written in microscopic dust. This delicate disk of gas and dust, the very cradle of planets, exists in a dangerous neighborhood. The young star at its center floods its surroundings with intense ultraviolet radiation, while even more powerful stellar neighbors can bombard the disk with high-energy photons. Left unchecked, this radiation would violently strip away the disk's gas, a process known as photoevaporation, rapidly dissipating the raw materials needed for planet formation. Here, cosmic dust performs a vital defensive role. The countless microscopic grains suspended in the disk's outer layers form a protective shield, a cosmic sunscreen that absorbs this harmful radiation before it can penetrate to the delicate interior. This dusty barrier is the disk's primary defense mechanism, preserving its mass and dramatically extending its lifetime. Without this shield, the window for planet formation would slam shut in a cosmic instant, leaving behind only a fleeting wisp of gas and a collection of stunted, unfinished worlds. The dust does more than just block light. It actively manages the disk's climate. By controlling how much radiation gets through, the dust regulates the temperature structure throughout the disk. This creates a tapestry of distinct chemical zones, each with its own unique conditions. In the cooler, shielded outer regions, water and other volatile compounds can freeze onto dust grains, creating the sticky ice that builds giant planets. Closer to the star, where the dust still manages to temper the heat, silicates and metals can slowly coalesce into rocky bodies. The very opacity of the dust, its ability to absorb and scatter light, is what carves out these specialized environments. It transforms a homogeneous cloud into a structured factory with separate assembly lines for different kinds of worlds. So while we rightly celebrate dust as the physical brick and mortar of planets, we must also honor its role as the guardian of the construction site. It is both the building material and the defensive barrier, a humble speck with the profound responsibility of safeguarding the future of entire solar systems. The same cosmic dust that built our solar system could one day fund our expansion into it. This is not science fiction, but a serious consideration for our future economy. Asteroids, those leftover piles of primordial dust and planetesimals, are not just barren rocks. They are treasure chests, rich with precious metals like platinum and gold, along with rare earth elements essential for modern technology. The concept of asteroid mining revolves around harvesting these materials, either to bring back to Earth or to use in constructing habitats and infrastructure in space itself. But the value extends far beyond metals. Perhaps the most immediately useful resource is water. Countless asteroids and comets are essentially frozen reservoirs, their dust grains bound together by water ice. In the vacuum of space, this ice is pure gold. It can be split through electrolysis into hydrogen and oxygen, the fundamental components of rocket fuel. Imagine a future where a spacecraft on a mission to Mars does not need to carry all its fuel for the return journey. Instead, it could stop at a depot in orbit around the Moon or Mars, a station that has manufactured its propellant from water mined on a nearby asteroid. This would completely change the economics of spaceflight, turning the solar system from a series of distant destinations into a connected network of resources. Even the fine dust itself, if we could find a way to collect it efficiently, might hold unexpected value. It could contain unique isotopes or exotic materials formed in stellar environments, substances with properties we cannot replicate on Earth, offering new possibilities for science and industry. While the engineering hurdles are staggering, the sheer potential is undeniable. The humble dust that once assembled our world is now poised to become the cornerstone of a new, off-world economy, transforming our past's building blocks into our future's most valuable assets. Our ancestors looked to the heavens and wove its essence into the very fabric of their stories. Creation myths from around the world speak of a universe born from a formless void or a swirling chaos, a poetic parallel to the scientific reality of a cosmos emerging from a primordial cloud of gas and dust. In these ancient narratives, gods and spirits often shaped the world from the soil beneath their feet, from clay or from dust itself, breathing life into the raw materials of the earth. This idea resonates powerfully with the biblical reflection that we are dust, and to dust we shall return, a statement that captures not an end, but a continuous cosmic cycle of transformation. The substance of our bodies, the matter of our planet, is all part of this eternal loop, borrowed from the stars and destined to be recycled again. This profound intuition found its way into modern culture long before telescopes could confirm it. The romantic notion of stardust, immortalized in song and literature, is more than just a beautiful metaphor. It is a cultural memory of a scientific fact, a deep-seated understanding that we are not merely in the universe, but that the universe is within us. When ancient sky watchers gazed upon the hazy band of the Milky Way, they told stories of a river of light or a pathway for spirits. They could not have known they were looking at the combined glow of countless distant suns, their light filtered and sculpted by immense, dark ribbons of interstellar dust. Yet their awe was perfectly placed. They sensed a connection, a kinship with the cosmos that our science has now put into words. Our oldest stories were the first draft of a truth we are only now learning to read, a testament to the human spirit's timeless desire to find our place in the grand story of everything. Despite our growing knowledge, the true nature of cosmic dust is still veiled in mystery. We have mapped its epic journey and witnessed its creative power, yet fundamental questions about its origins and behavior continue to challenge the brightest minds in astrophysics. The very first moments of dust formation remain particularly elusive. We know dust condenses in the cooling ejecta of supernova, but how exactly do those first few atoms find each other and cling together in the chaotic aftermath of a stellar explosion? What are the precise conditions that allow microscopic nuclei to form and then rapidly grow, defying the disruptive forces of the expanding blast wave? Answering this requires peering into an environment we cannot yet directly observe, pushing the limits of both telescope technology and supercomputer simulation. Another profound puzzle lies in the chemical richness of these grains. We have found that dust acts as a tiny chemical laboratory, but what is the full inventory of complex organic molecules that can assemble on its frigid surfaces? How do delicate carbon chains and probiotic compounds survive the violent birth of a new star, the journey through the protoplanetary disk, and the eventual impact onto a young planet like Earth? Their resilience is astonishing, and understanding it is key to grasping how the raw ingredients for life are distributed across the galaxy. The story of dust also changes dramatically across cosmic time and space. How does the dust population differ in a small, irregular galaxy compared to a grand spiral like our own Milky Way? And looking back to the early universe, what was the precise role of these first grains in the formation of the very first stars and galaxies? These primordial specks were the universe's first solid material, and their ability to cool ancient gas clouds may have been the critical spark that ignited the dawn of the cosmic lights. Perhaps the most tantalizing mystery is the identity of the carriers of the diffuse interstellar bands. For over a century, these dark lines in starlight have signaled the presence of an unknown substance, likely large, complex organic molecules clinging to dust. Unlocking their chemical identity would reveal a massive, hidden reservoir of cosmic carbon and complete a major chapter in our understanding of interstellar chemistry. Solving these puzzles demands a three-pronged attack: more sensitive observations from next-generation telescopes, advanced experiments that recreate the conditions of deep space in the laboratory, and sophisticated computer models that can simulate the life cycle of a dust grain across billions of years. Each new discovery about this seemingly simple material seems to reveal deeper layers of complexity, proving that the smallest builders in the cosmos hold the keys to some of our biggest questions. The journey to understand cosmic dust, it turns out, has only just begun. This grand synthesis reveals a cosmos more deeply interconnected than we ever realized. We have followed the journey of dust from stellar furnaces to the shores of newborn worlds, And through it all, one truth stands clear. Cosmic dust is the universe's ultimate connective tissue, the indispensable intermediary that weaves together every scale of existence. It is the quiet translator that converts the raw, explosive energy of a dying star into the tangible, solid foundations of new planets. It is the faithful courier, carrying the unique chemical signature of ancient suns across the light years and delivering that legacy directly into the swirling disks where new solar systems are taking shape. Its roles are breathtakingly diverse. It acts as a microscopic chemical laboratory, facilitating the reactions that build the precursors to life. It serves as a protective shield, guarding fragile young planetary systems from the very radiation that would tear them apart. From the grand sweep of galactic evolution down to the intricate dance of atoms on a single-grain surface, dust is not a passive bystander. It is an active, indispensable participant in the story of everything. This integrated view forces a profound shift in perspective. The epic tale of the universe is not solely about the brilliant stars and majestic galaxies. It is equally, and perhaps more fundamentally, about the trillions of tiny particles that move silently between them. These particles enable the very creation and evolution of the larger structures we so easily admire. The true, overlooked power of dust lies in this unique ability to link vastly different scales and seemingly separate processes into one seamless, unfolding cosmic narrative. It connects the death of one star to the birth of another, and the chemistry of deep space to the awakening of a living world. In the end, the story of dust is the story of a universe in constant, creative conversation with itself, building toward complexity one microscopic speck at a time. We began by reimagining the universe's greatest construction site, and we end with a profound appreciation for its most humble workers. Cosmic dust is far more than a cosmic afterthought. It is a master architect designing planetary systems with its unique properties. It is a chemical catalyst quietly assembling the complex molecules that make life possible. It serves as a protective shield, guarding infant solar systems from harsh stellar radiation. And it is a dedicated cosmic courier, faithfully delivering the elemental legacy of dead stars to the cradles of new worlds. This material built the very stars we admire and the solid ground of the planet we call home. It delivered the vast waters of our oceans and the iron in our blood, the calcium in our bones, and the carbon in every cell. The profound darkness you see between the stars is not a void. It is a canvas of potential, rich with the swirling seeds of future suns and planets, all carried on microscopic specks of ancient stardust. Let this knowledge settle not as a simple fact, but as a source of quiet wonder and deep connection. You are a living part of this grand cosmic cycle. If this journey through the overlooked power of cosmic dust resonated with you, we would be grateful if you shared your thoughts in the comments. What aspect of this humble material amazed you the most? For more explorations into the mysteries of space, please like this video and subscribe to continue the journey with us.